Okay. Welcome. Ágæta doktorsefni, góðir gestir, virðulega andmælendur, distinguished opponents. Ég heiti Andri Stefánsson. Ég held að þið kannski vitið flest hver ég er. Ég varadeildarforseti jarðvísindadeildar, verk- og náttúruvísindasviðs Háskóla Íslands. Og ég býð ykkur öll velkomin til þessar athafnar, þessar doktorsathafnar hér. Og hér mun fara fram Doktorsvörn, and now I'll switch to English. So today a PhD defense will take place. Hera Guðlaugsdóttir is going to defend her thesis, climatic fingerprint of volcanic eruptions. Hera Guðlaugsdóttir supervisor has been Árný Erla Sveinbjörnsdóttir, research scientist at the Institute of Earth Sciences, University of Iceland. The other members of the PhD committee are Dr. Hans Christian Sten Larsen. He is sitting here also in the front row, research scientist at the University of Bergen in Norway. And Dr. Jesper Scholte, research scientist at the University of Lund. He couldn't be here today. And Dr. Halldór Björnsson, group leader of the atmospheric research group at the IMO in Iceland, Veðurstofan. Hera Guðlaugsdóttir is born in Reykjavík. She obtained her bachelor degree from the Faculty of Life and Environmental Sciences in 2008. And after her bachelor degree, Hera worked as a biologist for some time before she began her master's study in geology that she graduated from in 2013 and then started her doctoral studies in 2014. So it means you've been 4 years. That's pretty good. So today Hera works at the Icelandic Environmental Agency as a climate specialist. So the opponents at the defense here, sitting here on my left, are Dr. David Shansettin, assistant professor of the University of Foscari in Venice, and Dr. Jess Nausbaumer. He is a research scientist at NASA in New York. And Dr. David, he is an assistant professor, as I told you before, in Venice. He has contributed to a wide range of subjects and is an expert in volcanic forcing and climate. And his current research activity consists of developing complex statistical models for the estimation of systematic errors of coupled climate models. This is very important, especially if you have experienced the weather in Iceland in the last few weeks. It's either tropical or polar, so there's definitely something happening. Dr. Jess is a research scientist at the NASA Goddard Institute in New York. He's an expert in water isotopes and climate reconstruction. His research focus is on climate and weather models, moist convecting and cloud physics, atmospheric hydrology, and global water cycle. And maybe that's something we have in common. So I'm thinking more of the deep water, you are thinking of the shallower water. So the PhD defense begins with that the candidate Hera presents her results of her thesis, following by examination of the opponents, who will discuss the thesis, ask questions, and you are supposed to answer. According to the regulations of the University of Iceland, others who are not opponents can also discuss the work of the candidate if they have requested so within 24 hours notice. And nobody has made any such request. So we'll just continue. So Hera, now it's your turn, okay? So you can present an overview of your research. And I suggest that we can just sit here in the front row, okay, and listen. Okay. Gangi þér vel.
So yes, hello, good afternoon. I'm glad to see you all here. My name is Hera Guðlaugsdóttir, and before I begin, I would like to express my gratitude towards the Department of Geology for deeming this thesis fit for a defense. I would also like to acknowledge my exceptional group of supervisors that I have been fortunate to work with. They are Árný Erla Sveinbjörnsdóttir at the University of Iceland, Hans Christian Sten Larsen from the University of Bergen, and Jesper Scholte from the University of Lund. And along with my supervisors in the PhD committee, then there is Halldór Björnsson. And I would also like to acknowledge, before I continue, our collaborators that also participated in this project, and they are Valérie Masson-Delmonte at the Science Laboratory of Climate and the Environment in France, Martin Werner at the Alfred Wegener Institute in Germany, and Bo Winter at the University of Copenhagen. And this is the structure of the lecture, where I will, for the next half an hour or so, introduce to you the project that I have been working on for the past 4 years. So the motivation behind this project sort of lies in my interest in understanding the interacting components within the climate system, the atmosphere, ocean, and sea ice, and how they react to volcanic eruptions. An exciting part of this was to approach the atmospheric circulation through the 4 main modes of the North Atlantic atmospheric circulation variability, not just one, as is common. For example, it has been fairly well established that equatorial eruptions impact the North Atlantic oscillation and cause surface cooling in the first years after equatorial eruptions, where the climate response can also be detected on seasonal to decadal timescales. Although North Hemisphere eruptions are considered to cause less global climate impact, their impact has been identified on seasonal to multi-decadal timescales as well. But during the initial stages of this project, a Holuhraun eruption began. And before that, then, of course, North Hemisphere eruption occurring during the polar winter were considered to have limited climate impact because of the sun being a limiting factor. But studies have shown that if Holuhraun, that began in the end of August 2014 and ended in the end of February 2015, and if it had continued a little bit into spring, then this would be identified as anomalies in the climate circulation or the climate variability. And this sort of underlined the need that the focus should be on both equatorial and high latitude volcanic eruptions. And this project has been divided into 3 parts, where the first part, the focus was on the study of the atmospheric circulation and the climatic response to volcanic eruptions, where the aim was to quantify the modeled atmospheric circulation response to volcanic eruptions by studying, as I mentioned, the 4 modes of atmospheric circulation variability in the North Atlantic. In the second part, the focus was on how stable isotopes respond to volcanic eruptions, where the aim was to assess these 4 modes in the stable water isotopes of precipitation around the North Atlantic, as well as in reanalysis data and models. The third task then focused on the volcanic fingerprint identified in Greenland ice core records, where the aim was to compare stable isotope records of Greenland ice cores with the results obtained in part 1 and 2, and to see if a common volcanic response could be identified. So the primary impact of volcanic forcing is that it shields the Earth's surface from incoming shortwave solar insolation. And that is due to the optical properties of SO2, or the sulfide aerosols, that form when SO2 in the volcanic plume reacts with water in the atmosphere. And by scattering this incoming shortwave solar radiation, this causes surface cooling in the first 2 years after volcanic eruptions. However, things get complicated when these same aerosols also absorb outgoing long-wave radiation from the Earth's surface, causing a warm layer in the stratosphere. This causes temperature variation both in the vertical atmospheric column, so the difference between temperature at the surface and in the stratosphere, but also in the meridional temperature difference, so the difference between the equator and the pole. And this can be identified as anomalies in the atmospheric circulation and pressure system within the troposphere. And a known example is the North Atlantic Oscillation. The NAO is the main mode of atmospheric circulation variability in the North Atlantic, where equatorial eruptions are known to cause an increase in the meridional temperature difference that forces the NAO towards the positive phase due to a strengthening of the stratospheric zonal winds. And this positive phase of the NAO causes a warmer and wetter climate in northern Europe and the east coast of North America, while the opposite occur during the negative phase. So prior studies have identified this NAO to be present in the first 2 years after equatorial eruptions, and a delayed NAO response emerging around a decade after equatorial eruptions has also been identified. Such a delayed response is considered to originate in dynamic ocean-atmosphere interactions. But as I mentioned earlier, the focus has not been on only one mode of atmospheric circulation variability, where we have taken other modes into consideration as well. In the North Atlantic region, there are 2 other modes that are important, and they are the Atlantic Ridge and the Scandinavian blocking, seen here. And along with the negative and the positive phase, they are an important part of the atmospheric circulation variability in the North Atlantic, where their fingerprint has been identified in the stable isotope records of Greenland ice cores. And in this figure, these weather regimes have been retrieved from the standardized 500 milliwatt geopotential height. And by standardized, I mean where the mean is set to 0 and the standard deviation is set to 1 without it affecting the structure of the data. So the yellow area is anomalies that are above average, and negative anomalies are below average. And this color scale you will see quite frequently. So by influencing the atmospheric circulation, other climate modes are affected as well, but on different timescales, where previous studies have shown that both equatorial and high-latitude volcanic eruption can cause a delay in the timing of the Atlantic meridional overturning circulation. where this overturning circulation can be considered as the Atlantic part of the ocean thermohaline circulation. Previous studies have also shown that equatorial eruptions can influence Arctic sea ice by increasing the sea ice extent. And this can further influence a planetary wave formation within the atmosphere that can have an impact on decadal to multi-decadal time scale that can be identified as anomalies in the atmospheric circulation. So the exact coupling within the climate system is not that well known. That is how the atmosphere, ocean, and sea ice interact within each other, where the memory in the climate system is considered to lie there within this interaction. But as I said, it's, their interactions is not well known. So the model that is used in this study is the atmospheric circulation model ECAM5. It is the atmospheric component of a larger Earth system model, the Cosmos Earth system model, where the run is from 800 to 2000 Common Era. The volcanic forcing in ECAM is implemented as aerosol optical depth and effective radius, where the main equations that are used to simulate the climate system in such Earth system models are, for example, the so-called continuous equations of fluid motion along with the physics of thermodynamics. Therefore, the results from such models are, in a sense, probabilistic. It's a probabilistic behavior based on theoretical behavior. So, as you all know, nature has its own way. So, it's really important to evaluate the model results using, for example, atmospheric circulation reanalysis and reconstructions, along with, as is done in this project, stable water isotopes. So stable water isotopes are usually expressed using the delta notation and are widely used within the climate community due to their unique ability to capture atmospheric circulation variability. And for example, stable isotopic records retrieved from polar ice sheets have revealed that stable isotopes are linearly related to temperature. And this has furthermore revealed the temperature variability spanning hundreds of thousands of years. However, this linear relationship is less clear in daily to monthly precipitation. And along with the atmospheric circulation variability, they also capture the origin of the precipitation, and along with the source conditions like relative humidity, sea surface temperature, and what is of interest here, anomalies due to volcanic forcing. And before I go into the main results of the papers, I would like to highlight some of the methods that were used. Sorry. So to extract the North Atlantic weather regimes, I used the K-means clustering, where the clustering method assigns clustering indices to each of the months that is clustered. And this allows for the calculation of the frequency of the weather regimes for some period of interest. And this was used, also this clustering method was developed further in order to retrieve the high-frequency atmospheric circulation variability in the North Atlantic, where a 50-year clustering window was applied on the whole data set that shifted every 5 years. And this represents the climate baseline retrieved for each weather regime that was primarily used in part 1. So in our search for a common volcanic signal or common volcanic response, I either use composite field analysis or superposed epoch analysis, with their only difference being that superposed epoch analysis is mainly used on two-dimensional time series, while the composite field analysis is applied on climatological fields. And it's a relatively simple statistical method that aims at retrieving, in this case, the volcanic signal through the climatological noise that is present through averaging. And this work has resulted in 3 papers that I will now discuss. The first paper, the focus was on the influence of volcanic eruptions on modeled weather regimes over the North Atlantic for the period of 800 to 2000 Common Era, where the results were obtained by stacking these equatorial volcanic eruptions and these North Hemisphere volcanic eruptions to retrieve their average volcanic response in the 500 millibar, 250 millibar pressure fields, the temperature at 2 meters, and in the first principal component of the sea ice extent retrieved from the empirical orthogonal functions. The volcanic eruptions are selected based on the volcanic forcing time series implemented in ECAM, the aerosol optical depth and the effective radius. For the equatorial eruptions, the forcing is prescribed in all latitudinal bands, while the North Hemisphere eruptions, it is only prescribed between 30th and 90th degree north latitude bands. And to assess the volcanic response in the 4 modes of the variability, the volcanic years of interest were retrieved from the climate baseline, where 2 years before an eruption to 20 years after an eruption were stacked using the SEAM method, revealing the change in the frequency of occurrence that you can see here in the y-axis. And here on the x-axis is the years, 2 years prior to 20 years after, where year 0 is the eruption year. The area within the green lines, the error bars, represent a climate that has limited volcanic forcing, and the years that go over or under these green lines are considered to be significant in the 95% confidence interval. The blue line is then the ensemble mean, and the gray is the 95% confidence intervals. And here, this is shown for the Atlantic ridge, the Scandinavian blocking, the negative and the positive phase of the NAO, along with the variability in the first principal component of sea ice. And according to these results, the Atlantic ridge emerges in year 2 after equatorial eruptions, that you can see here, as a result of volcanic surface cooling. And what is also significant here is the rise in the sea ice extent that remains significant until it reaches the pre-volcanic state here in year 12. What is also of interest here is the significant increase in the positive phase of the NAO in years 3 to 5 compared to the known response detected that is usually detected in the first 2 years. And this is present both in the clustering, that here, and the 250 millibar pressure fields. And this suggests ocean-atmospheric coupling that is more prolonged than yeah. And the atmospheric circulation response is also impacted in years 12 to 14, where this suggests a link between the atmospheric circulation and the sea ice response. So the results for the high latitude eruptions are less robust compared to equatorial eruptions, possibly due to the fewer eruptions selected for high latitude eruptions. However, a slight weakening in the 250 millibar zonal winds is identified, possibly as a result in the decrease in sea ice in year 3. But a little of significance is identified using the clustering method. And again, a weakening is detected around a decade after high latitude volcanic eruptions. And that emerges as the positive phase negative phase, of the NAO, and also as a decline in the sea ice in year 10. And now to the results for paper 2, where the weather regimes are studied in the delta O18 of winter precipitation. So further assessment was on the volcanic fingerprint is done by using the delta O18 from the global network of isotopes in precipitation, or GNIP, for the period of 1961 to 2012. This is also assessed in the delta O18 of ECCAM VISO to compare, or as a comparison. The 20th century reanalysis project is used in this part, where the volcanic signal in the 500 millibar pressure fields and the temperature at 2 meters were selected. To retrieve the average equatorial response in GNIP, 2 large volcanic eruptions were selected, the Eruption in 1982 and Pinatubo in 1991, where they are considered to be one of the largest ones in the 20th century. The criteria for selecting the North Hemisphere eruption is that they should occur during summer with little impact of other eruptions close in time. And this left me with few options, where in the end Hekla 1970 and Sarychev Peak in Russia were selected. And here you can see the global network, or the stations that are distributed globally within the GNIP network, but our focus is here again on the North Atlantic region. So by clustering the 500 millibar pressure fields from the reanalysis, clustering indices were used to extract the delta O18 winter pattern in precipitation from GNIP associated with each regime. However, to have a reference, the delta O18 pattern associated with each regime was also extracted from ECCAM, that represent the 1200-year average pattern. And here, the circles indicate the GNIP stations that are superimposed on this 1200-year average delta O18 pattern for the Atlantic Ridge, Scandinavian blocking, NAO, the negative and positive phase, where again these are standardized values, or the delta O18 anomalies. And according to this, these weather regimes are fairly well recorded in GNIP, although it's much clearer in the NAO. And the main results when it comes to the equatorial response identified is that the isotopic signal that is present in GNIP in the first 2 years seem to follow the positive phase of the NAO that is identified in the reanalysis. However, in years 3 to 4, there are some discrepancies that emerge that is difficult to interpret at this stage. For the high latitude eruptions, again, the response is weaker. However, the isotopes that is present in the first 2 years also show some link with the negative phase of the NAO that is identified in the first 2 years after high latitude eruptions. And again, this is less clear for year 3. And in the last paper, the volcanic imprint in the North Atlantic climate variability is studied in the isotopes of Greenland ice cores. And in this part, the volcanic response in the first 5 years is assessed in using 13 Greenland ice cores spanning the period of 1771 to 1970. And to study the long-term climate impact, I use longer isotope time series from 3 Greenland ice cores spanning the period 1241 to 1978. And due to scarce proxy data, the atmospheric circulation reconstructions of Jesper Scholte, my supervisor, et al. 2018 are used in parallel, where the reconstructed delta O18, the sea level pressure and the temperature at 2 meters are used. And the eruptions that are selected here to retrieve the average volcanic signal are based on the radiative forcing time series of Sigl et al. 2015. And keeping in mind here the figure of the average delta O18 response identified in ECHAM, depleted delta O18 anomalies or lower delta O18 anomalies should be expected over Greenland during the positive phase of the NAO. And when the equatorial response is studied in the average delta O18 from the 3 core average, which is the green line here, that is exactly what is seen here, where the blue lines are the upper and lower confidence interval, and the red line represents the 99% confidence level, and the dotted is, this is 95% confidence level, and this is 99% confidence level. And yes, this it becomes significantly lower in the first 4 years, and again in years 8 to 11. And when the NAO index is extracted from the first principal component of the empirical orthogonal functions, where the positive values indicate the positive phase and the negative values indicate the negative phase, that is also something that is seen, where the positive phase is present in the first 4 to 6 years, and again around a decade later. Considering the response after high latitude eruptions, little response seemed to be present in the delta O18 in the first 5 years, although the reconstructions do indicate the presence of the negative phase and the Scandinavian blocking. And when the NAO index is studied, it is, as you can see, it fluctuates quite much, but although the negative phase is present in in years 2 to 4 at least. And again, emerging in years 8 to 9. That is detected in all parameters. But as you can see, it becomes significant quite frequently. So, yeah. So to conclude, the main findings of this work is that equatorial volcanic eruptions, they seem to leave a more persistent response in the first 5 years that emerges as the Atlantic ridge due to surface cooling and as the positive phase of the NAO. That is evidence of a more dynamic coupling lasting longer than expected. And also in the modeled response, the significantly prolonged increase in the modeled sea ice also indicates a more prolonged dynamic climate impact after equatorial eruptions. The main findings for the high latitude eruptions is that the response seems to be in antiphase with the equatorial climate response, where while the equatorial response, while the signal, after equatorial eruptions is mainly associated with a strengthening of the zonal winds in the first years, we see evidence that there is a weakening present in the first years after high latitude eruptions, and therefore a more dynamic and prolonged response is identified. And also these results suggest that the sea ice is impacted as well through a decrease compared to an increase after equatorial eruptions. So when I zoom out from this project, there are many questions that remains to be answered, especially regarding high latitude eruptions. But I would like to list two. For example, the sensitivity of the Arctic sea ice needs to be addressed. So as opposed to the positive feedback equatorial eruptions can impact the climate system, could high latitude eruptions, for example, have a negative climate impact and therefore amplifying the current climate state we're in. It's also important to do some sensitivity tests for various scenarios of Icelandic volcanism, where many of the largest volcanic eruptions over the past 1,000 years occurred in Iceland. For example, Eldgjá in 940 here, Laki 1783 here, and these are examples of fissure eruptions that do not necessarily go up into the stratosphere, like Holuhraun as well, that only reached 4 to 5 kilometers up into the atmosphere. So these tests should address the column height as well as the duration of these eruptions. Although the focus point here has been on the climate system, it is important to remind at least myself that societies will be affected, and therefore it's important to be prepared. And with these words, I would like to say thank you for your attention.
Thank you, Hera. Very well done. So this finished the introductory talk of the candidate. Now it's the turn of the two opponents. So we'll wait for Hera. She's getting some papers and so on. Do you have a thesis?
Ha.
Ritgerð. Já, hafið eina ritgerð líka með. So who was going to, David, you were going to start, yes. And then following, yes. So you can use this one. Þú getur notað þennan, hérna. Svarað hérna. Þeir standa þarna. Okay, það allt í lagi?
Já, allt í góð.
Okay, can you hear me? Okay, so first of all, thank you, Hera, for the very nice presentation. Your thesis has quite an elaborated storyline, and you use quite different sources of information in the attempt to identify this volcanic fingerprint of climate variability. And actually, I would like to go back to the very title of your thesis. Yeah. So why did you choose the word fingerprint? Because in the detection and attribution community, it has a very specific meaning, right? And I think what you do here is really an important step forward in the characterization of volcanic impacts on climate. But I would like you to discuss a little bit more what we really need to do further in order to establish that these signals that you find are really fingerprints of volcanic forcing. And beyond that, why do you think fingerprinting the impact of volcanic eruption is so important for our understanding of climate variability?
Okay, thank you. Thank you. Yes, this is an interesting question regarding how I use the words.
Mm-hmm.
And I think, so in the beginning of this project, so this originated in my study of a shallow Greenland ice core from northwest Greenland, where I was really fascinated about the climatic fingerprint within the stable water isotopes. And therefore, this name sort of came in the beginning. But maybe if I would choose it now, maybe it would not be so dramatic, you know.
Okay. And why do you think fingerprinting is so important? What should be different in the fingerprint of volcanic eruptions compared, I don't know, to the imprint of solar variability or of anthropogenic greenhouse gas emissions? So why do you think this is relevant for the climate research community and also for the society to study volcanic eruptions? What is really important?
So for a couple of hundreds of years, we have been really fortunate, societies around the globe, that we have not experienced huge volcanic eruptions that can, destroy societies, at least after the Industrial Revolution, at least a couple of 200-300 years. And we have evidence of a really large volcanic eruptions that can have a really sharp and sudden impact. And perhaps what the focus has been mainly on, at least it is not until recently when, in the past 10 or 20 years, where the focus has been on the prolonged volcanic impact on the climate system. And I think it is important to understand that, because it can give us an insight into the climate system itself and how it interacts and how it stores information. And by studying these volcanic eruptions and the long-term climate impact and the difference between eruptions that are located on different latitudinal bands on the Earth, this can sort of quantify the climate system in more detail in order for us to sort of prepare and project possible future scenarios
and
of climate variability.
Yeah. So in this sense, I think that studying volcanoes is also important because it is a way through which we can evaluate the different tools that we have to understand climate.
Yeah.
So observations, we don't have many, right?
Yeah.
Reconstructions, we have different, but they come with the uncertainty from the reconstruction process.
Yeah.
And models that you were using.
Yeah.
And I would like you a little bit to comment on the use of climate models for investigating the response of climate response to volcanic eruptions, and more specifically about the climate model that you used. I think it is a very valuable set of simulations, but the model is admittedly not anymore a state-of-the-art.
Yeah.
So it is quite old. And so what can we really learn that is valid today and can test this, and can stand the test of further research with new models concerning the climate response to volcanic forcing?
So ACAM, the version used here, I did not do the run itself, but it is, of course, if I begin with the fact that it is a low-top model, so it does not capture the whole stratosphere and the important stratospheric modes of climate variability there. For example, the quasi-biennial oscillation. However, this model has been shown to capture the North Atlantic oscillation and the polar vortex strengthening associated with the NO quite well. But I am sure that, I mean, I'm itching my fingers to be able to use the climate models to see what this would show if it would have covered the whole stratosphere. And in ACAM, it is also known that volcanic cooling, or studies have shown evidence that volcanic cooling is most probably overestimated in ACAM. And this we identify, or this I identified in the study. But this still does not prevent the model to capture sort of the main behavior in the atmospheric circulation after volcanic eruption, since we are seeing known response as well. But I am sure this would be more detailed using like the state-of-the-art version, and of course comparing different models as well. I mean, that's also really important. This is only this is only one model, and not only is it just one model, we only have 6 ensemble members. And in the model community, that's not considered to be much, sometimes not hardly significant. So that is also an important part. But even though that is the case, it is interesting to see how results from ACAM compares to, for example, the Greenland ice cores. So, yeah.
So you touched different aspects. I would like to deepen a little bit.
Okay.
So, well, maybe the first aspect I would like to discuss with you is about your choice to use this weather regime approach, weather type approach, compared to the more classical approach where you just define this NAO or Eastern Atlantic pattern, which is based on this monthly mean data and some kind of EOF analysis or whatever. So I think there is a lot of value in your approach. The only thing that I was wondering when I was reading your thesis was why did you feel the need to separate the NaO plus and NaO minus as two separate modes? Whereas if I look, for example, at the spatial patterns that you also showed today, there seems to be quite some linearity in the two patterns, so they look more or less the opposite of each other. And so why you have a now NaO plus and minus instead of just one mode that is more or less prominent or has opposite phases?
Yeah, I mean, this is a very good point. I mean, so like in the initial stages, it was decided to go for the k-means clustering method to extract these weather regimes in order to estimate their frequency of occurrence, or to get sort of a frequency variability analog from ECHAM. And also to sort of understand if there is an antiphase between the equatorial and high latitude volcanic response. And I mean, if I would go back now to do it, I would probably compare these two methods. But I mean,
would you expect major differences or not really? Just by your feeling? Because, for example, this Atlantic ridge looks a lot like the Eastern Atlantic, and the Scandinavian blocking is also known to be part of this classical outcome of the UF analysis. So,
what could be, what the use of this method could result in is that the noise in the data could be decreased, and therefore the signal that is present maybe could would stand more out, because the clustering method it is of course noisy, because there are some cases where a specific month or year is assigned to a specific weather regime according to the clustering, where maybe there is nothing going on, nothing of significance that relates to that weather regime. You know, so for me it would only result in the fact that the real atmospheric circulation anomalies would stand out more clearer.
So then one of my biggest questions concerns this very tight phasing. I really like your results about this delayed response, you know, this prolonged response, which kind of hints towards some coupled mechanism being activated by the volcanic eruptions. Yet I feel the fact that you really get this tight phasing just 12 or 14 years after a major eruption, some significant signals pop up in the atmosphere, right? Whereas before you have just more or less some noise. And this is kind of surprising in a way, because if I think about an ocean-mediated mechanism, then I would see, or I would expect to see, a more tendential behavior, like a more smooth curve than you develop towards a certain anomaly. So, and this is surprising also because of the variety of eruptions that you consider. So you have Tambora, the 1258, but also Kuve, or eruptions that are very different. So what is, in your opinion, at least in the model world, a mechanism that really may be responsible for this tight phasing in the response, in letting an atmospheric response to emerge after a decade or so from the eruptions, while being so-called silent before that? Is that clear?
Oh, no, no.
So why don't you see a smooth evolution? Rather, you see some noise and then some significant signal popping up, which is the underlying mechanism that you would consider as the most likely responsible for such tight phasing in the response that at some point emerges.
yeah, so sort of what is my opinion of the resulting mechanism causing
Yes.
this yeah. So I am really I'm a fan of planetary waves. Where I think the sea ice plays also a very important role, both when it is increasing, but also when it again goes below, where the planetary waves are more relaxed, maybe. And this could cause, like this, for example, this strange signal we see in years 12 to 14, for example, like why 12 to 14, why not, yeah? And that, in my opinion, would be due to the sea ice, or the atmospheric circulation responding to the sea ice, either increase or decrease. And for example, an decadal signal like 12 to 14 years, that would be like the atmospheric circulation responding to the decrease.
Okay.
And the decrease in the sea ice would then also again be related to maybe to the thermal transport due to the AMOC.
Okay. Yeah.
That is my idea. But again, I am itching my fingers to like understand that mechanism better.
Yeah, I think that that might be something like, you mean the interaction between the sea ice response and the MOC, which are anyway interrelated.
Yeah.
And at a certain phase of this oscillation, you have the establishment of the right conditions for the atmosphere to generate this.
Yeah.
Okay.
Yeah. So that would like be like the secondary impact.
Yeah.
Okay. For the decadal.
Yeah. Okay, I understand. So then I would like to go a little bit more on the methodological aspect, because I think the value of your thesis is on the characterization, and the use of proper statistical method is very important to get robust results and make robust inferences. And I was a little bit surprised, I must say, by the choice of using the t-test, which is actually a parametric test and is based on the assumption of Gaussianity. Of course, it has a wider use, but I wonder why you didn't choose a non-parametric test, so without making any assumption about the distributions of your data. And I would like you to comment on that. Why would you defend your choice of using the t-test?
Yes, this is a factor in this work that I am aware of, so it's a really important point. In the case of ACCAM, the distribution of the data, I studied that a lot. And in the end, there were two possibilities for distribution: a log normal distribution versus a normal distribution, and the data fitted more the normal distribution. And in ACCAM, so that's why it was used. But
so you think that for the data that you used, you checked that they would fit a normal distribution, more or less. Okay.
But regarding like the small data set that I use, as I say, if I would like do it like again now, maybe I would compare different approaches. But for example, in GNIP and the Greenland ice cores, the main focus was like on the overall behavior of the pattern. Like, do we see a resemblance in the pattern that is present in the isotopes? Can we relate that pattern to a specific regime? Because it's difficult to estimate if it is like significant or not, because because the area of optimal retrieval to capture these weather regimes is maybe not where the ice cores that I have access to are.
Yes, I see the point. Yes, I agree. So, okay, I'm satisfied. I have just one last question. Okay. So concerning the outlook of your work, so what do you think it is most important to make a progress in our understanding of this volcanic fingerprint on climate variability? Do you think we need to improve the models? Do you think we need better observations, so waiting for the next big eruptions? Or do you think we need to improve our database of proxy records? Of course, we need all the three. But in the light also of this huge effort of the coupled model intercomparison project that you may be aware it's coming. So, yeah, there are a lot of experiments that will be devoted to understanding the response, the climate response to volcanic eruption. Do you think that's enough, or we really need something different than just improving our models?
I mean, like to improve the models, of course, then, I mean, we would need like, that is an interdisciplinary factor where a lot of scientists from different fields like mathematics, physicists would need to come in to like to improve the computational speed more or something like that. But at least after studying part 2 and 3 of this thesis, I am more aware that the climate community needs more proxy data because right now, especially over Greenland and in the Arctic area, we have very little data there, and that is the area that is most affected by volcanic eruptions, both equatorial and possibly high latitude eruptions as well. And right now we have limited proxy data retrieval there, except of course the Greenland ice cores are of course really important, but in order to get a more detailed understanding on the climate variability over the Arctic region, it's really important to capture that well and understand that well, because that will influence the globe.
Yeah. I agree. Okay. I'm happy. Thank you very much.
Great, so David covered a lot of what I was going to ask, which is good. So just to keep going on that sort of line of thought, and maybe it'd be helpful to pull up maybe that GNIP map versus the isotopes, or the model-derived.
That would be...
that's fine, actually. Well, no, keep going. That's good. Yeah. Hang on. Well, so if you, so one of the, actually collecting proxy records is difficult, right? So, but let's say you could get one site where you could collect any sort of proxy record. Where would you put it? And ignore technical issues about if it's feasible. Just there was an ideal location to target your question. Where would it be?
I mean, in the case of the the NEO is fairly well covered by GNIP, because at least in the significant areas where we see high anomalies and low anomalies. But in the case of Atlantic Ridge and the Scandinavian blocking, one of the things that I did here was to identify the optimal area to retrieve the Atlantic Ridge and the Scandinavian blocking, and that would be in the east Greenland here. So that would be my first location, to go there to get more data, but also like in the Baffin Bay area as well, like the Canada region as well. So.
Okay. Yeah. No, I would agree. Let's focus on northeast Greenland. So, why do you think isotopes have such a significant response in that area for these meteorological patterns? I mean, it can be a hypothesis. I don't expect you to know exactly. Yeah.
So if I would assume that the isotopes would follow the atmospheric circulation, like for some given average period, like a long-term average, then I would, as I say, go into this area. But on shorter time scale, that could not be the case. That perhaps would not be the case. So, for example, if there is like a season in which, for example, Scandinavian blocking would be common, I would perhaps this location would perhaps not be the best to retrieve the signal there for so short period of time. So that would also be needed to take, I would need to take that into consideration, like is it a long-term average response or daily to monthly response? Because then things really get complicated.
Yeah, right. Yeah. Okay, so then maybe I'm more flipping to, say, a modeling side. So, I mean, you looked at, obviously, like sea level pressure, geopotential height, isotope fields, air temperature, but, models can output hundreds of different variables in diagnostics. So if you could just add another variable to look at to try to better describe sort of the general climate or anything of your interest, what would that be?
So that would be, the primary thing that I would want to look into would be the ocean thermal transport. But then I would need to take into account radiation at the top of atmosphere and other parameters like that. But what I would really like to understand more is the behavior, like why is the response in the stable isotopes like I see? Like there is a link that is missing, I feel. And I think your suggestion on the water vapor in the atmosphere would be a very good idea to understand that as well. And also, and this was initially part of the part 2 project, was to study the deuterium excess. And I began studying that, but then of course you need to take into account relative humidity, sea surface temperature, and due to time limits and sources. I mean, it was really difficult to include all of that, but that would definitely be something that would be important to address in order to understand sort of, so how would the dynamical response be recorded in the isotopes as a result of ocean atmosphere coupling and so on.
Right. Yeah. Do you think as we discussed about the sort of decadal influence of, the sea ice and the ocean heat transport kind of inducing an NAO response, let's say. Do you think the isotopes, for example, are capturing just literally that NAO circulation, or do you think that they're also influenced by, because for example, when you change sea ice, you're changing the evaporation pattern of the surface. I mean, do you think that might have an influence on, so you could basically imagine there's kind of two different types of NAOs, right? One that's, let's say, I'm making this up, but one that's, purely atmospheric internal variability, and then one that's sort of forced by the sea ice ocean.
Yeah.
How did you, again, just hypothesizing, but how do you think that would influence the isotopic recording of those events?
Okay, so my initial thought on this, if I understand you correctly, is that, so let's say in the first 1 to 2 years after volcanic eruptions, we see a strengthening in the stratospheric winds that results in the positive phase of the NAO. Then I would perhaps expect the isotopes to, as my results show, is that they would sort of follow the atmospheric circulation, because that is also the case when there is no volcano. Then there is a strengthening in the stratospheric zonal winds that results in an NAO. However, this prolonged impact, or the dynamic impact after volcanic eruptions, so during these first 2 years when there is an NAO, and then there is of course a strengthening of the westerlies over the Atlantic Ocean, and because of the increased winds over the surface, that could influence the latent and sensible heat flux from the ocean, and this could result in at least this could be detected as anomalies in deuterium excess, at least. So this was something that I was really curious about, but unfortunately I didn't have time.
It's fair.
So did I answer your question?
Yeah. No, it's. So also then, I'm just kind of staying on the sort of modeling, and you kind of already described this originally. Like if you could do this again with whatever model you wanted, you would pick a high top one, and you would pick one where you could maybe fully coupled, so you could look at the oceanic response. How would you set about the forcing of that model? Let's say you could do the model run yourself. So you can do, just hypothetically, you can just say exactly how you want to do the model. How would you force the model? Like how would you kind of tell the model, okay, volcanic eruptions happened, and how would you have that volcanic eruption influence the radiative balance in the model? Does that make sense?
Yeah. So you're talking about an individual case where there is like, where I have a specific eruption in mind.
Yeah, let's say you have a specific eruption in mind, but maybe we can make one more specific, right? So we know that this ECHA model is just given basically prescribed aerosol optical depth and effective radius in the stratosphere. Would you just repeat that again, or would you try to, or do you think maybe there's a more accurate or realistic way of forcing the model? If you had that capability.
Okay, so this maybe this addresses my limitations of the fact that I have not worked with models, so I am not
Okay, yeah, well, no, that's fine. So let's back up again. Let's talk about, like, the real, let's actually just say, is that representation of just adding an aerosol layer, that's some prescribed radius, does that truly capture what a real volcano would do? Or are there processes that exist in a real volcanic eruption that are missing from just that prescribed setup?
I mean, of course, this is simplified, at least in the case of Akkam, where the injection is at 10 hectopascal height, and it usually assumes a relatively short period of injection, whereas this can vary in nature. For example, for Icelandic eruptions, like fissure eruptions, that can be ongoing for years. Sometimes they are in the troposphere, and then they go into the stratosphere, and then blah blah blah. So this and in these kind of eruptions, there can be periods where there is ash involved as well, but also sulfate aerosols. So of course, using the aerosol optical depth and the effective radius is of course sufficient, but sometimes maybe it's an oversimplification of the various types of volcanism that is present on Earth. Does it answer your question?
Yes, yeah.
Okay.
Right. And then I think I might actually mostly be done. But I guess I wanted to end on kind of one statement. If you could, I've been science communication, this is kind of brought up, where if you're talking to a non-science educated person and they just kind of want to know really quick, like, what did you discover in your dissertation, or what new knowledge did you gain? Like, what would that be in like a few sentences, talking to someone? Like,
yeah, okay.
Yeah, what have we now learned from your dissertation?
Yeah. Okay, so equatorial eruptions, they can cause a strengthening in the zonal winds that can be detected as weather anomalies, where the NEO, the positive phase of the NEO, is present over a longer period of time than maybe was previously estimated, or we see an increase in the frequency of the NEO almost 4 to 6 years after we have an equatorial volcanic eruptions. So that would be like sort of the main interesting point for the equatorial eruptions. Whereas because the decadal response, although we see interesting coupling or evidence for interesting coupling mechanism, it's really difficult to state that. And of course, I mean, you are an expert in like identifying the late NEO response. So that is something that it's difficult to say from this work. Regarding high latitude eruptions, I would say that we see a more latitudinally, so the wind systems are more latitudinal, that could cause more severe weathers in the North Atlantic regions due to a weakening in stratospheric winds after high latitude eruptions, as well as evidence for the decadal response that is opposite to equatorial eruptions.
Okay.
Okay.
All right. Thank you.
Yes, thank you.
thank you, David, and Jess, and Hera. Thank you very much. So this concludes the official examination of the candidate by the two opponents. And now it's your time. So if anyone wants to make a comment or ask questions, it's your time. Any questions or comments you want to make? Not you two. You already made the comments and questions. Okay. So then this officially then concludes the examination. And ladies and gentlemen, we will now leave the room, me and the two opponents, and you can just relax for a few minutes until we come back. Hera? Okay, thank you. Okay. So the following text has been documented and signed into the PhD Registry of the Faculty of Earth Sciences. Doctorate from the Faculty of Earth Sciences, Hera Guðlaugsdóttir, 8th of February, and now I have to turn around because I'm not allowed to take the document then, so I have to memorize it or write it down. By resolution of the Faculty of Earth Sciences, Hera Guðlaugsdóttir dissertation, Climatic Fingerprint of Volcanic Eruptions, has been approved for a doctoral defense in geology. The defense has been made, heard, and accepted, and we therefore declare Hera Guðlaugsdóttir a doctor in geology from the University of Iceland. So there are some documents, and so here, and then this one. This is the document from the university. It's in 3 languages, in Icelandic, English, and Latin.
Wow.
Okay. And then there is I don't know where's. You must hear that.
Okay.
And then we used to have flowers, but they're very impractical, especially if people live abroad. So now we changed to a book. So this is a gift from the faculty. So thank you very much. It's been very nice to have you here for the last 4 years. I hope to see more of you in the future. So there's no name, but I think it's a picture book.
Yes.
Okay. So thank you very much. Congratulations. So David and Jess, do you want to say something? Okay.
So thank you very much. It was a pleasure to be here and to be an opponent of Hera Defense. And I'm looking forward of seeing more research done by you and cooperating maybe in the future. Thank you very much.
Yeah, I also wanted to say thanks for inviting me and letting me be Hera's opponent. I do think this is interesting research, and I also want to give credit because in many ways I think this is very multidisciplinary, and I think it's actually very hard. And so you're willing to go into this area where, you know, you have to learn a lot of different things. A little bit is takes some courage. And so I also look forward to you continuing this and advancing it. And I also hope eventually collaborate and see your work out more in the future. So thank you.
Thank you. I'm really like, I will not cry. Thank you. But I would like to say that I'm really honored that you both were here or are here as my opponents, since I respect your work really much. And they have influenced me during this work. And also, thank you, Andri, for conducting the ceremony. It has been really, in the beginning I was kind of overwhelmed because of the formality, but it's actually quite nice to have it like that. And yeah, and also, of course, Árni or Hans Christian or Jesper, if you are here. I'm endlessly grateful to you and for your support during this time. And of course my family, Jón og Ísleifur og Flóki og Þrymur. Og bara, já, takk fyrir. Og ég bara, komiði endilega og fáið ykkur með mér, skáliði með mér og okkur á eftir. Have a drink with us in Askja after the ceremony. En já, takk.
Okay, so bara takk kærlega fyrir komuna. Thank you very much for your attendance. And as Hera said, there will be some bubble wine and other things to eat and drink on the 3rd floor in Askja. So if you don't know where to go, just follow someone in front of you. There is someone that knows where to go. So thank you again very much. Thank you very much. Takk kærlega til hamingju. Þetta eitthvað rosa kerfið maður. Þetta jarðfræði. Já, þetta eftir hann Sigurfinn. Þetta rosa flott maður. En hún ekki mjög praktísk í að lesa svona upp í rúmi á kvöldið, sko. Hún svolítið
þetta er svona kaffi.
Nókanlega, sko. Heyrðu, ef eitthvað frá okkur hér? Nei, þá erum við bara bæði.